Okay, so when you have three n members, what happens is uh, the linear scale or the sliding bar becomes a triangle, right? So you might have compositions along the two axes as well. For example, here you will have another composition, and here you will have another composition. I mean, individual linear variations of relatively relative enrichments of the two n members uh, along the one of the sides, right? For example, 1 and 3 in this case, right? 1 and 3 can behave like a linear scale, provided that number 2 component is 0 there, right? Similarly, if number 1 component is not there in that system, uh, that composition will be variable along this scale, right? Along this scale, 2 3 line, 2 3 line. Okay, so 2 3 line, that means you don't have any third component there, right? You don't have any third component there. So uh, this is all possible, and similarly you can have one or two variation as well. But since this particular component that we are particular compound that we are talking about, compound or mineral, whatever, right, naturally occurs with the three components, right? Three components. So therefore, in most of the cases, you will never find its composition along any of these lines, right? So if you have all the three components there, then it must lie inside the triangle, wherever, depending on the composition. Okay, so somewhere in the triangle, it depends on how much the component is there. For example, you can mark here 50, right? So this is the 50% mark along this line. Okay, similarly you can mark 50 here. Okay, so you can mark 50, and again you can mark 50 here as well, right? So if all the components are there in like 50%, for example, if you have number 2 component 50, number 3 component 50, right? So in that case, you you will have to denote it in a line like that, because number 3 component 50 is always going parallel to this opposite face, opposite side. Okay, and number 2, when you take this one, 50 composition is here, so it should go parallel to the third side, that means to this side. Okay, so you have the composition like that, and if you have the other one 50, right? So the other one 50, number 1, right? 50, then it should go again parallel to this, like this, right? So this is how the composition we can denote. So inside this, the occurrence of all the variations of that particular mineral can happen. But if everything is 50, right, you can't have a proper composition there, because the total composition should be 100%. But in this case, it's not possible, right? So that's why you don't find any intersection point. So if you want to denote any composition, I mean a naturally occurring composition, the real composition, actual composition, so when you plot them, you might get some composition somewhere here, right? So in that case, so you can find its composition by drawing a line parallel to the third phase, like we did before. For example, here, right? So you have here, okay, I will use another color. So if you have some composition like here, right, natural composition, when you analyze it and you get one, two, three compositions in such a way that when you plot it in the triangle, it comes over here. Right? So if you want to find how much number 3 is there, then you have to draw a line parallel to the third axis, right? So then you can find how much the composition of 3 there, right? Either from this way or from this way. Okay. Since this is parallel to the third line, you will get similar compositions on the both sides, right? So if you want to get the composition of, the percentage of number 2 component, then you have to draw a line like this, parallel to this one. So similarly, you have to draw another line parallel to this one, like this, for the number 1 composition, right? So there you can see how much number 1 is involved there. Okay. So likewise, we can find the composition, the percentage value for each component. Okay, so this is how 3 member compositions are denoted, and we can do this using Excel or some other triangular plotting softwares are there, for which are used for mineralogy and petrology calculations, right? So it's just a macro. It's for Excel. It's just a macro. You can run it and you enter the compositions. It will automatically it will automatically plots whatever you need in a triangular diagram. Okay, right. So if the components are just 2, then it's a binary composition, binary variation. If there are 3 components, then you can consider it as a ternary system, right? Binary system, ternary system, variations are available for different minerals, compositional variations. Okay, so we can see here 2 member compositions for olivine. You have olivine here, right? One side is iron, right? One side is iron, that is phthalate, right? So you have phthalate, and the other side is magnesium, which is phosphorite, right? Phthalate and phosphorite compositions are there, components are there. So the olivine composition can vary along this line, whatever the numbers, right? It depends on natural olivine sample that you collect, right? Different olivines will have different composition. Some are phosphorite rich, that means it should be above 50, right? If you want to say it's a phosphorite, then its composition should be above 50. That means magnesium composition should be above 50%, right? If it's phthalate, if you want to call it phthalate, then it should be iron rich, right? It should be above 50 iron. So this is how olivine compositions are shown, and you can see here if you want to add silica also into this system and show, still possible, but usually it is not necessary. This is just for your information only, because the solid solution behavior is shown by iron and magnesium only. Silica is not involved there, but in some cases, some minerals, silica can also involve in solid solutions, right? Especially like with aluminium, it's possible, but in this case, it's not necessary to show in a diagram like this, but still possible. Okay, still possible, because when high silica olivine and low silica olivine, like such variations are there, right? Some cases, some situations you might find silica variation depending on the crystallization condition of the olivine, right? For example, if olivine was formed in the mantle, right, at a greater depth, like greater depth means we have several depth levels in the mantle: shallow, moderate, and deep. So under shallow conditions, aluminium phase we have is plagioclase, right? Plagioclase still possible to occur in the mantle, right? Then when it goes to little more deeper, you will see uh, a disappearance of plagioclase and appearance of spinel, right? Because these are aluminium phases, plagioclase, spinel, all these are aluminium bearing phases. So this aluminium can replace silica. That's why this low silica, high silica variation, which might be observable, right? And if you go further deep into the mantle, what you will get is garnet. Okay, so you'll have garnet instead of spinel. Actually, this transition or this variation or this change is caused by olivine decomposition, right? So olivine reacts with plagioclase and form spinel. Again, at deeper levels, olivine reacts with spinel and then it forms garnet, right? So these are actually pressure sensitive reactions. Pressure sensitive reactions. These are normal reactions, but those are pressure sensitive, right? Wherever you have aluminum enrichment in the mantle, this can take place. So in that case, this silica variation can happen. So in that case, you can put silica also into the system, and then you can show instead the phaelite phaelite fosterite variation like this, right? And also you can show enstatite ferrocylite variation as well. What is enstatite ferrocylite variation? That is pyroxene solid solution, right? Pyroxene solid solution. Enstatite means iron rich pyroxene, and ferrocylite is magnesium rich pyroxene, right? So olivine solid solution and pyroxene solution both can take place, but you will see here those are taking place at different silica compositions, right? Silica composition levels. So for phaelite fosterite case, you see the silica component is low, right, compared to that of pyroxene. So that means for olivine stability, silica is not a big matter, right? It doesn't cause much difference whether silica is present or not, right? But normally olivine is stable under low silica conditions, right? Because uh, these compositions, right? So these compositions are determined mainly by this solid solution and not dependent on much on silica, right? But pyroxene, which has a different composition, uh, it is sensitive for aluminum presence, right? So therefore, it requires a lot of silica. So I mean, aluminum is replaced by silica. So in that case, it's a favorable condition for pyroxene formation in the mantle. Okay. So this is another, I mean, separate story, but just keep in mind that. Okay, so you can see here another solid solution composition, uh, which is phlogopite, lepidolite, muscovite. Right? You can add even biotite here, right? Because all these are mica. Right? You can add biotite also. Uh, but commonly you will see this common composition is there with OH hydroxyl component, right? These are hydrous minerals, and potassium is always there in between the layers, right? In between mica layers, you can remember the sheet silicates, right? Phyllosilicates, they are layered structure. So in between those layers, you will see cation. Cation is bonded, right? Usually monovalent cation like potassium. So in addition to these are the pure compositions actually, right? So you can have even iron and magnesium replaced there in variable amounts, right? So here you have the magnesium already. So instead of that magnesium, some iron can also come there, right? So in this case, two ions are there, aluminum and lithium. Lithium is monovalent, right? So aluminum is trivalent. So you know 3 plus 1, 4. So for that site, you can have either two the divalent cations or just different varieties or just one from the one type. Then you can have amphibole compositions, right? We call it actinolite tremolite series, right? Actinolite tremolite series. There also you can see this iron magnesium exchanges there, right, as a solid solution. And hornblende is very complex composition. You have monovalent and divalent here. Even trivalent or higher valencies can also be there. Right? This is amphibole or hornblende composition. So when these numbers are there in the formula, so this we call the stoichiometric numbers. Okay. So I think you know that stoichiometry is important for balancing the chemical equation. Okay. So we will see here now another triangular diagram which denotes feldspar composition. Okay, so feldspar composition, you know, feldspar is composed mainly of sodium, calcium, or potassium, right? All the other things are common. Aluminium, silicon, or silica is common. Okay, right? Sodium, calcium, aluminium. Sorry, potassium. Right. So sodium, calcium side, sodium, calcium side. That means this particular side is represented by plagioclase feldspars, right? So the sodium N member composition we call albite composition. Okay, this is the albite composition, and calcium N member we call plagioclase. Okay, calcium N member is plagioclase. So in principle, here it's 50. So if calcium is above 50, then commonly you can call that particular feldspar as a plagioclase feldspar, right? If it is less than 50, or in other words, sodium is greater than 50, then you can call it uh, albite, albite composition, albite, albitic feldspar, right? So even this sliding bar, right, can be divided into several feldspar compositions. Some names are there: albite, oligoclase, andesine, labradorite, pitonite, and anorthite. Right. So all depend on the amount, right? So you can graduate this scale, and you can categorize them into several subgroups, right? Plagioclase feldspar, several subgroups. But in the case of orthoclase, that means potassium feldspar, mainly potassium feldspar, that is usually restricted to this area. Okay. The potassium feldspar is usually restricted to that area. That means it's like above 75 of potassium. Okay. Sodium is just about up to 25% only, right? Because from there onwards, nothing. From there onwards, no sodium. Okay? So there are some very high temperature varieties of feldspar uh, which can occur along this line, along this zone, right? Along this zone, some very high temperature feldspars can occur. Otherwise, uh, it might be blank, right? That means no feldspar occurring in that region. But anyway, within this region, there are no feldspar compositions, right? This blank white area represents feldspar absent composition. In the world, you don't find any feldspar composition which can fall into this zone, right? So that means it's a forbidden zone. That means no feldspar compositions, nothing. Okay. uh, Another diagram, the same diagram with some other categorize some other subgrouping. So you can see the radioactive feldspar subgroups similar to the previous one, but here you see some sub divisions. Actually, orthoclase is limited to here. There is another one has come here, shown here, that is sanidine. That is called sanidine. Actually, this is very high temperature, right? So that's why in the previous diagram, it was shown in a zone like this. Actually, it all depends on the experimental conditions, but most of the experiments have shown this high temperature feldspars are favorable in this area, okay, in this region, right, rather than occurring all throughout up to here, right? It can happen, it can occur even here, but not very common, right? So naturally occurring sanidines are falling in this area, okay. So additionally, you can see some miscibility gap, right? Miscibility gap there. Uh, that's what I mentioned, no feldspars compositions, right? So usually there are no such feldspar composition found. So this is the feldspar solid solution diagram, which shows you different n member compositions. Okay, different n members. N members are these corners, edges. Any question? Please enter your number, registration number in the chat box, right, to mark the attendance. Okay, so we will go ahead. Okay, so we will see the composition of uh, what? The composition of garnet solid solution group as well, right? As you know, it's a sorry, it's an isosilicate. It's an isosilicate, and uh, so you can see some solid solution behavior in garnet as well. Particularly, you can expect magnesium, manganese, and iron, ferrous variation there that we call Pyryl spite group. Pyryl spite group because of this one. Pyral spite. Pyryl spite. So this is just for your reference. We call it pyryl spite group, and the other one is ugrandite group. Right, ugrandite group, because the components occurring there is oroite, grossular, and rhodite. Right, so it's ugrandite. Okay, so pyrope is magnesium rich end member, and almandine is iron rich end member, and spacetine is manganese rich end member. Right, so this is pyrospite. And then you have the ugrandite solid solution compositions in the triangle, where you have grossular composition, which is calcium rich in member garnet, and then you have the androdite, which has both calcium and iron, right? Both calcium and iron, because it was not available in the pyrospite. Okay, and then you have oroite, oroite. Composition, which contain both, not both, all iron, magnesium, and manganese compositions. Okay. So actually, since you have several cations involved in the solution for a single component like this, right? It's very hard for you to show each and every element in the triangle with one face, like here. Here only one element, one element. But this is very difficult because it is. I mean, you don't have enough dimensions there, right? So in this case, you have to take the all three dimensions, x, y, z space, right? To denote only the urovite composition, not the whole ugrandite composition. And then you have again calcium end member here, and the other side calcium and iron end member here, right? So therefore, they are represented as the mineral uh, as the mineral itself. Okay, so without taking elements out from there. Okay, so because of the complexity, but of course there are some computer models which shows different elements, how they are replaced, that you can model, right, in three-dimensional space. So usually these compositions are, I mean, we see just iron, manganese, and magnesium variation diagram, right? Not as the whole mineral diagram like shown here, but we can still show them, or we can simplify these diagrams just to show the element or atomic composition, right? You can have magnesium, iron, magnesium, and manganese. For these three varieties, that is also possible, right? So make it a planar diagram in one plane. All these compositions are measured using the EPMA facility, electron probe microanalyzer, like SCM, like instrument, right? Even SCM you can use compositional measurements, but the thing is it's not precise enough for quantitative analysis. For qualitative analysis, no problem, but for quantitative analysis or quantitative representation, uh, the precision given by SCM is not enough. So that's why we do not use it for quantitative analysis. For example, for like when you have to calculate the PT values, PT conditions, pressure, temperature conditions, you have to go for thermobarometry, right? Thermometry and barometry together we call thermobarometry, right? So for that, you have to use uh, chemical equations, balanced chemical equations, and for such applications, you need uh, very precise elemental compositions. For that, you have to go for a electron microprobe, right, rather than SEM. And using those compositions, we can construct uh, these diagrams because we get to know about the atomic compositions. Okay, you can again see here another triangular diagram which shows pyroxene compositions. Shows pyroxene compositions, and you will see enstatite, ferrocylite here, enstatite and ferrocylite compositions, and then you have the wollastonite composition. Okay, so what is wollastonite? What is wollastonite? Is it a pyroxene? Yeah, there is a little defect in the wollastonite structure, right? It's not a real pyroxene, right? It is a pyroxenoid. It's one of the pyroxenoids, right? I think you can remember we did these things. Okay, so you see, this is a graduated diagram, not like the previous diagrams. So those are sketch diagrams, but this one is a well graduated diagram. You can see from 100 to 0 representation, and from 0 to 100 representation here, and also you have 0 to 100 representation for wollastonite and ferrocylite side, this side. And you see here pigeonite compositions, right? Pigeonite, augite, diopside, Heidelbergite. So this is normally called diopside Heidelbergite series. Again, you have a miscibility gap here. You don't see normally pyroxenes in this range. And when the composition, the solid solution composition increases above 5%, right? Above 5% here, the calcium component, when it goes to above 5.7, sorry, above 5%, we term it a clinopyroxene, right? Otherwise, it's orthopyroxene, right? So that's also different, and you have to keep in mind that. And for example, here, see, when it come to middle to down, right? You have high calcium at the beginning and low calcium in the second, in the latter case, right? Because uh, when you have a lot of like I mean iron and magnesium enrichments, they are extremely extremely favorable conditions for iron and magnesium exchanges. uh, Usually it tends to form orthopyroxenes, not clinopyroxenes, because clinopyroxenes need a significant amount of calcium, right? So here you see about 20 is necessary. So about 20 means it's a significant amount within the crust. So for that clinopyroxene to occur, you need that composition. And pigeonite, but actually pigeonite does not occur in all the way from here to there. Normally pigeonite occurs like this. Okay, it's like bulging curve. You can draw a bulging curve also there. which contains the occurrence of pigeonite, worldwide occurrence of pigeonite. I mean, it doesn't mean that pigeonite cannot occur with compositions like this, right? It can, but it's not commonly happening. Okay, it's not common to happen. Okay, any question related to this diagram? Because we have just shown only compositional representation of these diagrams. I will provide some notes of these lectures later on, even for previously taught content. But it's very important that you get extra knowledge from other sources, right? So that's very important because just by listening to these facts, which I'm here to say, is not sufficient for you, right? Because you have to thorough this subject uh, by yourself, right? Otherwise, you will never grab all the important points, right? Because some facts are there, especially related to these ionic replacements or site assignments, crystallographic site assignments. You have to read a lot, some textbooks, and capture the knowledge, right? That's why you are here in a university. So you have to explore the knowledge. Okay. 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 So then we will move to another important point, some of the another important points where we will consider uh, what are the factors that influence the solid solution. Okay, the compositional variation in minerals. Actually, this compositional variation is mainly caused by solid solutions, right? Because it's not a reaction, right? Always remember, solid solution is not a reaction. It's just a replacement only, but it takes place without physically damaging the mineral. That is also important. In the case of a reaction, you might see some physical variations, right? Physical changes, right? If biotite changes to sillimanite or something, then definitely physically you see appearance of sillimanite there, right? As a result of consumption of biotite. So that means originally available biotite is missing now, right? So this is a physical change. But these reactions, solid solution reactions, are not physically happening because once the reaction ends, also you see the same mineral, right? Not a different mineral. Only difference is the composition, right? Instead of iron, you might see enrichment of magnesium there, right? So it's not a real physical change. It's only compositional change happening. So in our definition, we mentioned that a mineral must have a definite composition, but not necessarily a fixed chemical composition. Remember that, right? Definite composition means, for example, if you want to talk about olivine, then you know olivine contains iron and magnesium, right? Iron and magnesium is a must, right? Sometimes you might see only iron, sometimes you might see only magnesium, but mostly you will see iron and magnesium for olivine. It does not have calcium or it does not have manganese or something like that, right? So that means uh, it's definite that you have iron and magnesium, but this iron and magnesium we are talking about can be variable, right? It's because of solid state solid solution reactions, right? We already talked about that. We talked about magnesium replacement by iron, iron replacement by magnesium. So that means the original composition or whatever the composition you have changes, right? So originally, I mean, at one stage, iron may be 50%. At another stage, iron may be 20%. So now the composition has changed, but it doesn't mean that olivine has disappeared or it has formed another mineral. No, still olivine, right? Even at 20%, you have olivine. You had olivine at 50%, right? So it means definitely uh, not fixed composition, right? Although it's definite, but it's not fixed composition. So that's why we mention about this type of terminology for our definition, right? For the definition of a mineral, right? So solid solution means not necessarily fixed amount of uh, element or iron or whatever, right? That's what related with solid solutions. So in very simple ways, the chemical compositional variation in minerals is referred to as solid solution. So that is the very simple definition or introduction you can give for solid solutions. Chemical compositional variation in minerals just is referred as a solid solution. So factors are there for the solid solution to take place, right? But this is what happens ultimately. Okay, right. But another important thing is, although we say it's solid solution, it's not really a solution, right? It's not really a solution because when almandine converted into pyro, right? You don't see any melt or liquid formation. You never see liquid phase generation, right? But we still say it's solid solution because it's like a mixture, right? Solution is also a mixture, right? So sugar solution means you add sugar to water and mix it well, right? So it's a mixture. So likewise, iron and magnesium is added to the component and mixed in different proportions, and it is variable upon heating or upon pressure or whatever the physical conditions change. So that means that particular solid also can behave like a solution or a liquid material, right? So that is what you call solid solution anyway. Okay, so let's see why this solid solution happens in rocks, right? Uh, it's because all the rocks around us uh, are very solid material, right? And composed of at least one or two minerals, right? So these rocks are subjected to various pressure and temperature conditions within the earth interior, I mean in the earth's interior. So as a response to this PT variation that is recorded or that is suffered by the rocks which contain minerals, uh, is again very important, right? So the changes happening in minerals. So that is what we talk about as solid solutions. So some factors essentially control the amount of solid solution that can take place in a given rock system, right? So that is also very important fact. What is the first one? The size of the ions, right? So that is important, the size of the ion, because if it does not fit into the structure of the mineral, I mean size wise, right? So it won't happen, right? The reaction or whatever the thing does not take place. So the size is important. If it is the equal size or almost equal size, then you can put it as a solid solution there, but because the size matches with the mineral structure. Okay, so the crystallographic site, the size matters there, right, to substitute elements. So the same size atoms, if you have same size ions, if you have to replace each other, it happens very rapidly, right? So garnet is a good example. Iron and magnesium replacement is very stable in garnet structure. At the same time, in other minerals also, if it is iron and magnesium, because both are divalent and same, almost same size, so it's very easy for the structural replacements. If the cation is too large, then it does not fit into the site, right? Because in the structure, in the mineral structure also, or the lattice actually, you must have some space for these replacements, right? Because it's full of atoms for this strange magnesium coming from outside. To accommodate, there should be some enough space. So that is also controlled by these physical parameters as well as the deformation conditions, right? So they all depend on the ultimately on the pressure temperature conditions, which makes some vacancies within the crystal lattice. Why deformation is important? It's because deformation makes some stable lattice unstable, right? The stress-strain relationship. There, you might see some vacancies due to loss of existing cations, right? So, to such sites with vacancy, new ions can go into uh, and fit it very well if it is of the same size. If it is different size, large size, then it's a big problem, right? But if it's small, then still no problem. It can bear the situation because it is small. The strain, the outside atom is smaller than the crystallographic site. So the size matters, right? Is one factor, and the other one is the charges on the ions that are substituting for one each other. Okay, the charges on the ions that are substituting for each other. If the charges are same, then the crystal structure can remain electrically neutral, right? So if the charges are same, like for example, if in the situation of let's say olivine, iron and magnesium replaces, right? So what about the charges? To replace iron or magnesium, there should be two or divalent anion there, right? Divalent anion means like two having two as the charge, right? So iron and magnesium is also two divalent, so it can fit into the structure very well. If the valency or the charge does not match, that also a problem. But for example, for olivine, you can't put in chromium because chromium is 3 plus. The valency is 3 plus, so chromium cannot go into olivine structure. But some very rare situations are there. We will talk about that later. When such mismatching cation is replaced, some situations allow to replace, right? There will be some additional charge, right, without neutralization, right? For example, if forcefully you try to put some aluminium there, aluminium is 3 plus instead of sodium or iron, which is 2 plus. Once replaced, you will end up with extra 1 plus charge, right? Extra 1 plus charge because of aluminium 3 plus, right? Because the site was only suitable for 2 plus, right? So then to neutralize that molecule, you need one more replacement, right? Because you have 1 plus remaining there. So likewise, neutralization doesn't happen when mismatching ions are trying to replace, right? So, but they anyway, uh, the exact charged ion should replace the molecule for having a stable molecule at the final stage, right? If it is not neutral, then it is not stable also. So that's the point, right? If a molecule is not neutral, that molecule is metastable. Might be metastable or completely unstable even. Metastable means like in between, stable and unstable, in between, right? It can be stable for some time, but soon it will become unstable, right? So that is what we call the metastable. Okay, and the third factor is very easy that you know already. It's temperature and pressure, right? So under which the substitution takes place. So that is also important point, not just the temperature and pressure, the ambient or the prevailing temperature and pressure conditions under which these replacements are taking place. One important fact related to this is the high temperature conditions. Right? So I always indicate you at high temperature and pressure conditions, high temperature conditions, these solid solutions are very active. Right? These solid solutions are very active because the reason of the diffusion. The diffusion makes everything very agitated, right? Under high temperature conditions. So it's easy for the ions to move around at higher temperatures. So that's why uh, there is a lot of replacements or substitutions are taking place under uh, under high temperature conditions. Right, so the main reason is written here. You can see here because the atoms vibrate at higher rate. Okay, that is one of the main important factors. And also there can be some angstrom level expansions. Some angstrom level expansions can be there. Okay. I can see a question there in the chat. Does oroide contain chromium? Some resources says its composition is calcium, chromium. Yeah, that's possible. This is what I'm just now mentioning. When it comes to higher temperature conditions, right? When it comes to higher temperature conditions, what happens is some of the sites, crystallographic sites, get expanded, right? So it allows higher valencies to replace. So in this oroide, chromium 3 plus can come into the structure in that case, right? So it all depends on at what temperature these minerals crystallize. Crystallization temperature is the important thing, not just the prevailing temperature. Remember, when the crystallization takes place, during that time, these replacements can take place. At the same time, other replacements are happening throughout the evolution of the rock, but normally when higher temperature conditions prevailing, there is more tendency for these large cations to go into the structure, right? So that could be one of the reasons where this high atomic or high valent cations are going there into the structure, right? Is it clear? That is possible. Yeah, good question. That's all. Okay. The vibration is also important, right? The vibration of atoms. It vibrates largely, and it makes the lattice sort of strained, like, right? So that it makes some kind of expanded space in between atoms, so that other large cations can come into. And also at higher temperature, if the deformation is also taking place, because the rocks are always subjected to high stress conditions within the Earth's interior. So that makes automatically them to be deformed, right? So folding, for shearing, like deformations. So these deformations can cause some crystal lattices also to deform, right? Not just the rock deform, it can deform the crystal lattices also. It's not happening always though, okay? But it can happen, right? So in that case, you will end up with the distorted lattice, distorted ion. So these distorted ions can replace some, different cations. I mean, they might not be matching with the valency, but because of the defect, uh, you will have very large site crystallographic sites that could accompany some or accommodate some larger cations. That is possible. Okay, so the temperature is very important because of that. Pressure is not much affected, but it can still give you some facilitation, uh, uh, since it can change the size of the crystallographic site, right? If it is highly compressed, then the crystallographic site is small. If it is loosely compressed, that means low pressure conditions, then the sites are more free, so that this solid solution can take place easily, right? So at lower pressure or higher pressure, and higher temperature and lower temperature, all these facts can affect their crystallization condition. Okay. Okay, so we'll see the different types of solid solutions, right? So there are three, basically there are three solid solution types. So we call them substitutional, interstitial, and omission. So these are the three varieties, three types, three categories of solid solutions. So what are these substitutional solid solution? It's the most simplest solid solution that we have already talked about. It's very simple because they just replace each other. The atoms just replace each other, right? For that, it's necessary to have equal charge and nearly equal size to happen this very smoothly, right? So equal charge and nearly or equal size atoms. We can't find exact equivalence anyway, but at least nearly equal size is necessary for these substitutions. Okay, so this is a simple substitution, uh, substitutional solid solutions, right? So it's a one variety of solid solutions. And since this solid solution is very effectively taking place uh, because of the similarity of size as well as the charge, right? We call this solid solution also sometimes as complete solid solution, right? So you might see in the literature some wordings like that, complete solid solution. That means entirely simple substitution has taken place. And it can also change some situation, like if the sizes are similar, but in some situations some very different substitution can take place, uh, but usually it happens in a limited range of compositions, right? So that means uh, although uh, equal size and equal uh, valent cations are trying to replace, the replacement does not go very smoothly, right? Sometimes it might be affected by another factor, third factor. Probably the lattice might be deformed, defected, like that, right? So in that case, the lattice may be highly stressed, although you have the same size, same valency with the vacancy there, but internal energy or some other factor might be influencing for the solid solution. So in that case, it might not be completely happening. So such solid solution, if it is like that, we call partial solid solution or limited solid solution. Okay. And it's also possible, yeah, actually it's mainly dependent on the environment, right? Environment means the strain condition, or the whether it is under stress or under defect or under defects. We call these defects, we call crystal defects, actually crystal defects. uh, Sometimes we call dislocations also, dislocations, right? You will learn about these things under structural geology separately. Okay. These are some deformation related terms. But anyway, if the solid solution is not completely happened within the system due to a third factor, such as highly stressed atom or highly defected that lattice, or not sufficient pressure or temperature conditions, that means under low temperature conditions, solid solutions are not very much favorably happened, right? So they are partial solids. In the such cases, partial solid solution is very common, right? So the solid solution does not happen completely. So you can see some common examples in this table. For example, the iron magnesium substitution, right? Usually this substitution is very, very efficient and it is complete, right? At high temperatures, magnesium, more and more magnesium coming into structures, that is much more favored, right? So all these minerals, olivine, pyroxene, biotite, tremolite, ferroactinolite, these hornblanes, all these are influenced by iron magnesium solid solutions. And you can see the ionic radii of ferrous and ionic radii of magnesium. See, 0.78 and 0.72, almost same, very, very similar, right? And valency is also same, 2, right? And the size is also same, right? So therefore, this is very, very stable solid solution, right? Complete solid solution, provided that you have enough temperature, right? That is the third factor influencing, right? So if it's low temperature, might be some partial solid solution is taking place. Iron manganese, you can see the again the sizes, right? Manganese, how much? 8 3. Ferrous is 7 8, right? Not very big difference there, right? Not matching as iron magnesium, but not bad anyway, right? So complete solution can take place. And also, if the amount of manganese is limited within the system, then the solid solution might not be complete. Right? It can make limited or partial solid solution depending on the manganese composition. Because you know, in a rock, normally we don't expect manganese in excessive amounts. Iron, magnesium, calcium, aluminium, sodium, potassium, these elements are in excess amounts, I mean in sufficient quantities, because many minerals are composed of these said elements. But manganese is not very common, right? It's found in only very limited number of elements, but also not in big abundances, right? So therefore, uh, that unavailability within the environment of that element can cause a solid solution to be partial also, right? For manganese case. So some example here, carbonate. In the case of carbonate, siderite, rhodochrosite can substitute can take place. Siderite is iron carbonate, rhodochrosite is manganese carbonate, right? So this is a very pinkish mineral. You may have seen it in the mineralogy lab. We have it, very beautiful pink. Or pink is it? Yeah, yeah, like pinkish mineral. Okay, so you check with the magnesium 0.72 and manganese 0.8283, right? It's a little bit, the difference is a little bit larger, so it may cause partial solid solution, right? We can't find a very, I mean, we cannot easily find natural examples for that, for magnesium and manganese replacement, right? Possibly spacetine, garnet can might provide you uh, some as some example, right? And sodium potassium solid solution, sodium potassium replacement, right? Where can this happen? This can happen in alkali feldspars, right? Alkali feldspars, because potassium and sodium. Sodium size is 1.18, potassium size is 1.51, right? Still there is a little difference. So it might not be very, very, what? Very, what is it? I mean, smoothly not taking place, right? So you have to increase the temperature in the system to make it happen more smoothly, right? So high temperatures, uh, it can be complete. Otherwise, it's partial. So that's why you can remember uh, the triangle, feldspar triangle. There you don't see this solid solution happening. It was limited to some area here, right? That is another reason for that, right? Because you had sodium here, uh, sodium here, and potassium here. Remember, the solid solution is not complete always, but at high temperatures it can be, right? So alkali feldspars, you have this kind of composition, autoclaves, OL white. And then substitution, it can happen ferric and aluminium, both are trivalent. And you can see the size here, 0.65 and 0.54. Although the valence is same, the size has a difference there, clear difference there, because I mean, the difference between the numbers might be little or less, but still, when you have a high valency there, you can see some contraction within the nucleus, right? The higher the proton number, so such facts also affect this thing. So therefore, it does not allow these two elements to be in complete solid solution, right? So it provides only limited solid solution conditions there, right? Again, alkali feldspar is one of the examples, because you have aluminum there in the alkali feldspar, in the feldspar structure, which is 3 plus, and ferric sometimes can go into that structure, that place, that aluminum site. When it comes to halogen, bromine and chlorine, they are very closely matching sizes, the ionic radii, and also the valency is same, but the valency is low enough so that it won't give any problem for having it complete solid solution in the system. KCl, KBr, right? You can have this complete solid solution. And you can consider OH and fluoride also. The fluoride size is 1.31, OH size is 1.38. So that means it's very easily happening the complete solid solution, because this is just -1, so it's not big enough to affect the lattice, right? So in biotite you can have this replacement very easily. Instead of OH, you can have halogen, right? We talked it before. But in the case of halogen here, bromide and chloride, and if you consider the fluoride also there, you see the size difference, 1.31 fluoride, right? These are 1.96 or 1.81, right? So they are not matching. So therefore, you might not, I mean, there can be a solid solution, but not much expected. Okay. Right. Okay, any question? Do you have any questions regarding this content? Is your LMS working properly? Are you guys accessing that? Have you accessed LMS recently? Learning Management System of Faculty of Science, LMS. You can log in. No problem? Okay. Okay, right. So we'll move to the next topic, that is coupled substitution. Previously, we talked about only just single substitution. That means iron for iron magnesium substitution, or for chloride bromide substitution or something like that, right? So it's a single substitution, but there are situations where you can have two substitutions taking place at the same time, right? Concurrent substitutions, so two substitutions, so therefore we call it coupled substitution, right? So usually this coupled substitution happens when an ion has a different charge to substitute with another, right? So sometimes the size might be similar, so therefore it's possible for substitution. But once substituted, you will realize that the charge is different. So that means instead of a neutral atom, you get some charged atom, right? Either positive or negative. So in that case, to minimize that charge effect or neutralize that charge effect, another atom similarly charged ion will come into the structure, right? So then it neutralizes. So that is coupled substitution. That means two substitutions are taking place together. So another substitution has to take place in order to maintain charge balance, right? This is just to maintain the charge balance, right? These are common in silicate minerals where aluminum is involved in substitutions, right? We talked about aluminum involvement is not much like silicon also, but I said under certain conditions this aluminum can replace silicon in this in the lattice, right? So once aluminum goes to silica place, what happens? Size wise they both almost same, right? But silicon is 4 plus. Silicon is 4 plus because it is not connected to any oxygen there, right? I mean, it's a released silicon, not a tetrahedral. I mean, attached to silica tetrahedral, right? No oxygen is attached there, or even attached, it's broken. Okay. So when aluminum substitutes silicon 4 plus, what happens is 1 plus extra charge will be there. Okay, extra charge will be there. So to minimize or to neutralize that 1 plus, some other monovalent cation, monovalent ion has to come into. Okay, right. So here, if you consider silicon substituting aluminium, right? Silicon substituting aluminium, you get 1 plus extra charge, and oh, this is not exactly correct. Yeah. Anyway, the idea behind is just to neutralize it, right? So normally, what you have to do is to make it equal. For example, no, sorry, this is correct. This is 2 plus, this is 3 plus. Okay, it's 5. And this is 4 plus, and this is 1 plus, it's 5, right? So it's okay, right? Two substitutions are okay, right? So, yeah, which that is happening in plagioclase. This is happening in plagioclase. This is completely happening because calcium, aluminium, sodium, silicon, all are, I mean, matching sizes and valencies. I mean, mainly like I mean, no uh, extra strain is created after substitution. So therefore, naturally, it is kind of a spontaneous action that happens as a complete substitution, right? But in this case, dioxide in pyroxene, right, and jadeite. composition, right? Because jadeite is sodium bearing. Right? Sodium, aluminium, calcium, magnesium, right? 2 plus 2 plus 3 plus 1 plus. Okay, 4 4. It's coming, but size wise, these ions are not matching very well. Therefore, it can be a limited substitution, but still, couple substitution is happening. Uh, again, these five plus. So here you have 4 plus 4, 8, right? Because this is two ions there, right? So there is no charge balance here, right? There is no charge balance here. So in this case, you need another atom, another ion to neutralize, sorry, this set, to neutralize this charge effect. You need some extra atom to include there, right? Because this is 5, 3 plus 2. And here, actually, this is 4, right? This is not 2, it's 4 because you have 2 here. 4 plus 8, right? So 2 divalent cation is required here to make it balance. This is happening in spinel. So normally this can be iron. Replacement is iron, ferrous, right? For 2 plus. For this extra 2 plus, we get iron, right? So then, I mean, it is exchanging for the other side also. Or otherwise, you can make it just no, this is very complicated because this is an extensive solid solution. I mean, it is happening extensively. Actually, it's it's a continuous solid solution, which is beyond our scope of our our syllabus. So I don't want to explain much on that extensive type of solid solution because it's like happening like stepwise like this, right? This solid solution reactions, which is called extensive type of solid solutions, right? Usually in spinners this happens because spinel can change variably depending on the temperature and pressure conditions, right? So its composition can largely be variable from low temperature to high temperature, from low temperature to high temperature conditions. So therefore, it's a little bit complicated type, right? So I think you need not to take this example into your consideration much. Okay. Any question about this couple substitution? Another important point related with this couple substitution is this sometimes this coupled solid solution involves filling of a vacancy, vacant site, just to achieve the charge balance. For example, the example given here is amphibole, tremolite. So aluminium 3 plus can replace 4 plus silicon. So as we discussed before, there you need 1 plus more for the balancing. So that is made by sodium plus going into the vacant site, right? So usually this is happening when this couple substitution takes place. So if you have vacant sites within the within the molecule, it's very easy for this coupled substitution to take place because the excess cation can easily accommodate in that vacant position. Okay, so then the formula would be changing like this, right? Because the sodium is coming into the structure. Okay, so you see here, sodium came to the structure. So sometimes you can call it sodic amphibole, right? Because it contains some sodium after the substitution. Okay, anyway, don't take much concentration on extensive solid solution. Right? If you get a time, we might discuss, but otherwise not necessary. Okay, so couple substitution is this, and then we have interstitial solid solutions. That is one solid solution type. Uh, so far we considered about substitutional solid solution. Okay, this is number one, the types of solid solution. Substitutional, we discussed that, and now we are coming to interstitial solid solutions. So interstitial solid solutions means it's not, I mean, some places there are some voids in the structure, in the atom. Sorry, in the lattice. Voids means some vacant spaces. So sometimes any ion can occupy there, not just to charge balance like in the previous case, right? Here, the vacancy of the void, the same thing, can be replaced by a atom which is meant for charge balance, right? So that not that one we are talking about. Just a single substitution in this case, right? So just it can accommodate a vacant site, right? So these are called interstitial solid solution. No specific varieties that we have to discuss under that, but just keep in mind some lattices are having vacancies or voids. That means without any atom there, right? It's just a hole like that, right? So such molecules we call defected molecules or lattice defected crystals. In such crystals, this can take place, right? This is what we call the interstitial solid solution. Interstitial solid solution. And then we have, this is second one, and we have the third one, omission solid solution. Omission solid solution. What is omission solid solution? This occurs when an ion of higher charge, an ion with higher charge substitutes for a lower charge ion, right? It is something like this. The lower charged one is like here, right? So let's say L, higher charged one is here. Sometimes, although this lower charged ion low in charge, right? This is charge wise. I drew the diameter. Okay, higher in charge this one, and low in charge this one. But these two might be of the same size, right? These might be in the same size, same size. But when it replaces the other, the size is okay, but the charge is there, excess charge is there, right? Sometimes this can happen, right? So lower charged ion can replace a higher charged one. Again, you will have a charge balance issue there, right? Because one is high charge, the other one is low charge, right? So in order to maintain the charge balance in this case without replacing, I mean, there may be no other element to be replaced also into the lattice, because there may be no space in the lattice to replace, although there are available second ions for a couple substitution like here, right? So couple substitution will not take place here because there may be no enough space. So then what happens? The one of the other site there. So this higher charge ion will occupy only one place, but another adjoining lower charge place, this atom will go away, omit. It will be expelled, like so. That is what you call the omission. So you will get some space there, and also you are getting reduced charge instead of that. So in that case, uh, two, I mean, instead of one large cation, one large atom, two small charged ones will be coming into the reaction there, coming into the action there, right? Not a reaction actually. So that will occupy there one side, and the other side will become vacant at the same time, right? So in such situation, we call it omission solid solution, right? So if you read it again carefully, this one, omission solid solution occurs when an ion of higher charge substitutes for an ion of lower charge. So you have lower charge here, you have higher charge here to substitute. So in order to maintain the charge balance, because you are getting a higher charge one, two of the lower charge ions will be replaced. Two of the lower charge ions will be replaced there, right? But the higher charge ion will occupy only one side, right? So that will come only into one side. That's what I mentioned here, as one is omitting, right? The other side become vacant, right? So it is like omission. One side is just omission without any other additional replacement is taking place, right? Like in the couple substitution. So you can take an example here. Uh, a feldspar is given as an example, microcline, right? In which lead 2 plus replaces two potassium sites, because lead is large, lead is big, so it can replace two potassium sites. So when replacing this, it comes only into one site, as we said before. So one of the potassium sites is only replaced by this lead 2 plus. The other one is just left behind, vacant, right? So that is what is happening in omission solid solutions, right? So only three types of solid solutions are there. The substitutional solid solutions, interstitial solid solutions, and omission solid solutions. These are the three types of solid solutions we can have, right? So even these substitutional solid solutions, you can have commonly happening as complete or partial. Complete or partial solid solutions can be there in the case of substitutional solid solution types. In the interstitial solid solutions, what happened is uh, just I mean voids or vacancies. Voids are replaced. It is just one of the voids is filled there, so that's why it's called interstitial solid solution. right? In the case of omission solid solution, always remember the highly charged one is coming to the small charged side. So they replace only one and the other one is just omitted there. Okay, so these are the main types. So additionally, under the simple substitution or under the substitution of solid solution, you may have couple substitution just to make the lattice balanced in uh, in the charge wise, right? So you can take this as a actually as a reaction is charge balancing for the purpose of charge balancing, right? Both sides should be of the same charge, right? If it is not same, then corresponding cation should again come into the uh, structure so that it is called coupled substitution because both substitutions are taking place together, right? Not one after the other because at the time of replacement, the system knows that they are not matching. So therefore, uh, instantly the other substitution also takes place. Okay, this is about solid solutions. So I think we have to stop here for today. But I suggest you that you go to some extra exploration of the same content, and I will make available these recordings also little later. Okay. I think Dr. Dharmapi will be taking up from 11. So you can continue after a short break with Dr. Dharmapi. I don't know whether he has sent you a separate link. I think he has sent you a separately link for from 11 to 12. Okay, do you have any question? If you have a question, I think okay, we may we will discuss it the next time then, right? So you can have a break. Okay.